The DX is ready to roll in. I'm hearing it at the bottom end of 20 meters. Oh, wait a minute. You've got to have your extra to work this portion of the DX band. Well, you'll be on your way shortly because we are more than 2/3 of the way through our material. More than 2/3. Congratulations. We're looking at practical circuits, of which 7 exam questions will come out of 7 groups. So let's jump right into E7A01 and ignore this DX that's beginning to pour in on the bottom of 20 meters until after you pass your upcoming test. Okay, here we go, E7A01. Our first question out of 13 deals with a bistable multi-vibrator circuit. What is it? That's called a flip-flop. And exactly how many output level changes are obtained for every 2 trigger pulses applied to the input of a T flip-flop circuit? 2. 2 trigger pulses, 2 output level changes. Now here's a good question. The frequency of an AC signal can be divided electronically by what type of digital circuit? Well, that is the bistable multi-vibrator. How many flip-flops are required to divide a single frequency by 4? Well, that would be 2. Since a flip-flop has 2 stable states, you'll need 2 flip-flops to divide a signal frequency by 4. Got it. E7A05. What is the characteristic function of an astable multi-vibrator? Well, the astable multi-vibrator alternates between 2 unstable states. What are the characteristic functions of the monostable multi-vibrator? Well, it switches momentarily to the opposite binary state and then returns after a set time to its original state. What logical operation does an AND gate perform? All right, what is a logical an AND gate? All right, an AND gate. An AND gate produces a logic 1 at its output only if the inputs are a logic 1. Now remember, the AND gate has 2 or more inputs with a single output and produces a logic 1 at its output only if all inputs are logic 1. Now, the way to remember this is remember AND, all, and the number 1 looking like the letters L for all. Got it? Okay. How about the NAND gate? Well, the NAND gate is like, no, it produces a logic 0 at its output only when all inputs are logic 1. What logical operation does an OR gate perform? Well, the OR gate will produce a logic 1 at its output if any input is or all inputs are logic 1. What logical operation does a NOR gate perform? Well, it produces a logic, remember it's a NOR or has an O in it. It produces a logic 0 at its output if any input is or all inputs are logic 1. Now, all of this deals with the truth table. And would the question pool committee give you a truth table on the exam? No. Nope, you got to keep it all in your brain. The truth table is a list of input combinations and their corresponding outputs that characterize the function of a digital device. I say let you use the truth table. That would help during the test, huh? In a positive logic circuit, what level is used to represent the logic 1? Well, if it's positive, it's a high level. Negative logic circuit, the level 1 is a low level. Think of negative as low down. Now, you'll have 1 question out of 13 on AND gates, NAND gates, NOR gates. So go over this portion of the audio course, and then let's move ahead and take a look at amplifiers. E7B01. Amplifier circuits, Class A, AB, B, C, amplifier operating efficiency, and all that. Here we go, E7B01. For what portion of a signal cycle, it's tough to say, signal cycle, does a Class AB amplifier operate? Well, the Class AB is more than 180 degrees, but less than 360 degrees. Now, the amplifier that has the highest efficiency may not be the cleanest spectrally, but the highest efficiency is class C. Where on the load line should a bipolar transistor common emitter class A power amplifier be operated for best efficiency and stability? Well, with this type of amplifier just below the saturation region. This is like your brain right now. You're very close to saturation, but just think you're at best efficiency. How can parasitic oscillations be eliminated from a power amplifier? Don't turn it on. Oh, no, no, no. Eliminating parasitic oscillations, you would neutralize the amplifier. So by neutralization, we can eliminate parasitic oscillations. Now, what about harmonics? How can even order harmonics be reduced or prevented in transmitter amplifiers? Well, we would use the push-pull amplifier. Push-pull amplifier will help minimize harmonics. What can occur when a nonlinear amplifier is used with a single sideband phone transmitter? The answer is ugly distortion. Sometimes FM amplifiers are employed up on the 2 meter and 432 single sideband portion of the weak signal portion of the band, and they sound terrible. So always make sure and use a linear amplifier when operating SSB. Non-linear amplifiers, those like for FM, are okay for FM, but not sideband. How can a vacuum tube power amplifier be neutralized? Well, the way we do that is we feed back an out-of-phase component of the output back into the input. What is the procedure for tuning a vacuum tube power amplifier having an output pi network? Well, the pi network is a good one, and what we do is we alternately increase the plate current with the loading capacitor and dip the plate current with the tuning capacitor. Boy, weren't those the days of tuning up? And when you do tune up, make sure you don't tune up on top of someone else who's carrying on a QSO, because you have to tune up once you get rolling on an active antenna, because that's what you're tuning up is to the antenna, by increasing the plate current with a loading capacitor and then dipping the plate current with a tuning capacitor. Now take a look at figure E7-1. Yeah, looks like a NPN transistorized type of circuit because the little arrow is not pointing in. What's the purpose of R1 and R2? Reminds you a little bit of Thevenin's theorem, doesn't it? Well, we don't have that anymore on the extra test, but R1 and R2 form a voltage divider to set the voltage and the current at the base of the transistor, so that is for fixed bias. R1 and R2 fixed bias. Now, looking at figure E7-1, and for the visually impaired, you don't have to look at it because they won't give you this on the test. But in the figure E7-1, the purpose of C3, well, let's take a look. One end of the capacitor 3 is connected to the emitter of the transistor. The other end is grounded. It is across in parallel with R3, so it must bypass AC signals around R3 to ground. So we'll call this an emitter bypass capacitor. Emitter bypass. What's the purpose of R3? Well, that was for self-bias, because the current through the R3 produces a voltage drop that affects the base emitter bias voltage. Now, since the transistor's collector and base current, that's the emitter current, determine the voltage at the emitter, it's called a self-bias. What type of circuit is this that we're looking at? It's called a common emitter amplifier. And in the figure E7-1, what's the purpose of C1? Oh, there it is, C1, that's the input coupling. It's in series with the input, so it's an input coupling capacitor. It will pass AC, that's the signal, but block DC from getting into the voltage divider or the base of the transistor. Now let's take a look at figure E7-2. Now, another NPN circuit. What's the purpose of R? Well, R is the emitter load. One end of the resistor is connected to the emitter and the other end is grounded, emitter load. What's the purpose of C2? Well, that is output coupling. Notice the little circle after C2. This denotes the output of the circuit. What's the purpose of D1 in the circuit shown in this figure? Oh no, a new figure, figure E7-3. You'll need to look at it in my book. There it is. In figure E7- I couldn't find the D in the other figure. In figure E7-3, D1 is a voltage reference because D1 is the voltage regulator Zener diode. And we use that to provide a voltage reference for Q1. Now, if the load current increases, R2 gets smaller, the output voltage would tend to decrease. And when the voltage change is compared to the reference voltage across D1 by Q1, Q1 adjusts its voltage drop from collector to emitter to raise the output voltage to the design value with a new load current. So D1 is a voltage reference. What's the purpose of Q1 in the circuit? Well, Q1 in the circuit, it increases the current handling capability, Q1. What's the purpose of C2 in the circuit shown in E7-3? Let's see, C2. Oh, there it is. Oh, that's easy. That is a bypass capacitor that bypasses hum around D1. Now, what type of circuit are we looking at? This is a linear voltage regulator. And imagine this entire circuit on a little teeny chip. Components D1 and Q1 give the answer away, a linear voltage regulator. What's the purpose of C1 in the circuit shown in E7-3? Well, C1 is a filter of the supply voltage. It's probably an electrolytic filter capacitor which removes ripple frequency from the input voltage. And boy, oh boy, when those wear out and go pop, they make quite a noise. What is the purpose of C3 in the circuit shown in figure E7-3? Well, C3 is found in power supplies. This is an RF bypass capacitor, keeping any stray RF energy from getting into the circuit, which would cause it to go into self-oscillation and probably blow up. C3 prevents self-oscillation. Couple more. R1 in the circuit. R1 supplies current to D1. R1 is connected to the power supply input voltage and supplies the bias current to operate D1 and Q1 at a stable operating point. And finally, R2 in the circuit, E7-3, R2 provides a constant minimum load for Q1. And I know I can see those eyes completely slammed closed. You're going, that's it, I'm out of here. I can't, I might have 10 questions on this. No, this is E7B23, which means out of this B area, E7B 1 to 23, how many total questions could you have on the test? Just one. All right, now let's take a look at impedance matching networks in E7C, beginning with E7CO1. How are the capacitors and inductors of a low-pass filter pi network arranged between the network input and output? Well, let's see. In a low-pass filter pi network, we have a capacitor that is in parallel with the input, another capacitor in parallel with the output, and an inductor in series between the two, and it looks like the letter pi. What's an L network? That's a network consisting of an inductor and a capacitor. A T network with series capacitors and a parallel shunt inductor has which of the following properties? The T transforms. T for transforms, all four answers have transform in it. It transforms impedances and is a, here it is, high-pass filter. So a T network is a high-pass filter. Think of T for TV. Remember that high-pass filter when you had an old outside TV antenna? Man, that was a long time ago. Well, anyway, TV, T, it transforms impedances and is a high-pass filter because that's what you used to put on the old TVs. What advantage does a pi-L network have over a pi network for impedance matching between the final amp of a vacuum tube transmitter and multiband antenna? Well, the key is multiband antenna. What do we remember in the technician and general class tests about a multiband antenna? They are ripe for radiating harmonics. So the advantage of a pi-L network over a pi network is the pi-L has greater harmonic suppression. How does a network transform one impedance to another? The answer, it's magic. No. The answer is to transform one impedance to another, it cancels the reactive part of an impedance and changes the resistive part. So it cancels the reactive part, that's a network, and an impedance, and changes the resistive part. What filter type is described as having ripple in the passband and a sharp cutoff? Wow, ripple, all right? That's the Chebyshev filter. Just like the word looks like and sounds, Chebyshev, it has a little ripple. Chebyshev, ripple. Got it, okay? What are the distinguishing features of an elliptical filter? Well, elliptical has an extremely sharp cutoff with one or more infinitely deep notches in the stop band. Elliptical. What kind of audio filter would you use to attenuate an interfering carrier signal while receiving an SSB transmission? Well, here we are down on the 40-meter band, and you know what happens on 40 meters. In the early evening all the way through the next morning as you're tuning around, you get these steady tones. There's one. There's another one. There's another one. Well, where are those tones coming from? Well, they're coming from Europe because we share our band with European AM broadcast stations. And let's say we wanted to pick up a station right here where we have that nasty tone. Well, watch what I do. I'm going to turn on my notch filter. Notch filter on. Now I'm going to adjust the notch filter. There it is. The tone's almost gone. And newer radios have an automatic notch filter, and if I'm real careful, I can notch that out. There's the filter in, out. Makes quite a difference, doesn't it? Well, that's the automatic or the manual, as in my case, notch filter. The notch filter attenuates an interfering carrier signal. What characteristics do typical SSB receiver IF filters lack that is important to digital communications? Well, IF filters lack linear phase response. So this is why many times when we're using digital communications, we use digital signal processing or digital filters. IF filters lack linear phase response. And what kind of digital signal processing audio filter might be used to remove unwanted noise from a received SSB signal? That's called an adaptive filter. Here's a signal coming in that we've tuned in with an adaptive filter. We're going to tighten it down a little bit more. Now, chances are you're hearing the pitch of that tone change slightly in characteristic, but not in actual pitch tone. And that is working with the DSP circuits and able to pull digital signals, CW as well as regular digital signals, out of the noise. That is the benefit of an adaptive DSP filter. Now, what kind of digital signal processing filter might be used in generating an SSB signal? We call that the Hilbert transform filter for generating SSB. And what type of filter would the best be used on the 2-meter repeater duplexer? Well, this is not DSP. This is a big cavity filter. We use cavities as 2-meter duplexers. The pi network, that's a network consisting of one inductor and two capacitors, or two inductors and one capacitor, looking like the Greek symbol P for pi. What is a pi-L network? That's a network consisting of two inductors and two capacitors. And which type of network provides the greatest harmonic suppression? See those same old questions coming back again. That is the pi-L network. Now, before we get on with oscillators and things like that, let's take a look at digital signal processing. I encourage all of you extra class soon-to-be hams, or I should say hams soon-to-be extra class, to think about a DSP system, either a radio with it or a DSP add-on circuit. Here we are in the bypass mode, tuning into the Maritime Mobile Net, and I'm going to go ahead and add digital signal processing. Here we go. Processing on. I'm going to turn it up a little bit more. It's really cleaned up the signal versus, hear all the noise in the background? Watch this. Without, with. So it makes a big difference, digital signal processing, especially on CW and the digital modes. On voice, yeah, you can hear a little bit of difference when I click it in for voice. Without, with, and with extra amounts. So yes, DSP circuits work well. So I encourage you either get an add-on box. I'm working with the AOR DSP multimedia terminal here at my recording studio, but there are many. There are speakers, Amcom, with the DSP built right in. So think about DSP as part of your upcoming extra class ham shack. And now let's take a look at the three major oscillator circuits used in amateur radio equipment. They are the Colpitts, the Hartley, and the Pierce. Colpitts, Hartley, and Pierce. Now for oscillators to oscillate, we have to have this, and that is we must have positive feedback sufficient to overcome losses. And that's what I'm doing right here on this tape. I'm giving you positive feedback that you're going to do just great on your extra class test. Now, how is the positive feedback coupled in the Hartley oscillator? Well, think of the letter H, and that is much like a coil with a tap in it. So Hartley is the tapped coil. Now, Colpitts oscillator, feedback on the Colpitts is through a capacitor divider, and there's only one answer with capacitor and Colpitts. So think of C for C, capacitor, Colpitts, and positive feedback in the Pierce oscillator. Think of Pierce always with a quartz crystal, and that is how the positive feedback is coupled in the Pierce oscillator. Anytime you see a Pierce oscillator, think of quartz crystal. Colpitts, that is capacitive divider, and the Hartley is through a tapped coil. What type of oscillator circuits are commonly used in a VFO? Well, in VFO, we use Colpitts and Hartley. The Colpitts oscillator uses a big capacitor and a variable frequency oscillator, and is the most common on older radios. Newer radios, even though they say they have a VFO, are really digital controlled via an optical reader. Now, why is a very stable reference oscillator normally used as part of a phase locked loop frequency synthesizer? Well, we need a very stable reference oscillator because any phase variations in the reference oscillator signal will produce phase noise in the synthesizer output, and we don't want phase noise. So we use a very stable reference oscillator. Now, what is one characteristic of a linear electronic voltage regulator? Well, the conduction of a control element, that is element, not element, is varied in it's just as tough for me to record this as for you to listen. The conduction of a control element is varied in direct proportion to the load current to maintain a constant output voltage. And that's what you want to look for on the examination, is constant output voltage, because after all, they're asking you about a voltage regulator. So if you get a test question on the extra exam and you just can't figure it out, look for some keywords that might agree with what's in the question. What is one characteristic of a switching electronic voltage regulator? Well, they're called switchers, and that is the control device is switched on or off with a duty cycle automatically adjusted to maintain a constant average output voltage. And here we go, constant average output voltage, and the word in the question, voltage regulator. What device is typically used as a stable reference voltage? Reference voltage. And a linear voltage regulator? Well, anytime you see reference voltage, be thinking of that's right, Zener diode. You're doing great. You're calling out these answers before I give them to you. What type of linear regulator is used in applications requiring efficient use of the primary power source? Well, for most efficiency, we use a series regulator. Everything passes through on the series regulator. Now, if you're not so worried about efficiency, what type of linear voltage regulator is used in applications requiring a constant load on the unregulated voltage source, like something coming off of a solar panel? There we would use a shunt regulator. And usually the chassis acts as the heat sink. Gives off some heat, and that's lost power. Shunt regulator. Which of the following Zener diode voltages will result in the best temperature stability for a voltage reference? Well, we try and get as close to 5.6 volts is considered the ideal voltage for a zero change in the temperature coefficient of a Zener diode, 5.6 volts. What are the important characteristics of a three-terminal regulator? You see a lot of those, and you see a lot of them getting replaced in radio equipment. And they get replaced because we overheat them. It's that little three-legged dark module on the side chassis of your equipment, using the equipment chassis as the heat sink. Well, the most important characteristics of that three-terminal regulator would be maximum and minimum input voltage, and maximum and minimum output current, and maximum output voltage. The other three answers look identical to this answer, so be careful. Maximum and minimum input voltage, maximum and minimum output current, and maximum output voltage. What type of voltage regulator limits the voltage drop across its junction when a specified current passes through it in the reverse breakdown direction? Again, that is called the Zener diode. All right, you're making good progress. That was 15 questions, of which how many will be on your test? Only one out of E7D section. Now let's go to E7E modulators, reactance modulator, phase balance detectors, mixer stages, and frequency synthesizers. Let's tune in to E7E01 F3E FM.
Horrendous amount of gain and everything, but it's got this...
Yes, it's F3E FM voice, and we produce FM with a reactance modulator on the oscillator. Keyword, reactance modulator, but more keywords, on the oscillator. Reactance modulator on the oscillator. Now, how does a reactance modulator work in an F3E FM signal? Well, the reactance modulator acts as a variable inductance or capacitance to produce FM. How does a phase modulator work? Well, it varies the tuning of an amplifier tank circuit to produce PM, or phase modulation signals. Now be careful, those two answers that say phase modulation signals, the other two say AM signals. It varies the tuning of an amplifier tank circuit. So P for T, phase modulation tank circuit. Now let's tune in to single sideband phone and see how we can generate a single sideband phone transmission. Oh man, they're working DX down in the extra class portion of the band. Hurry up, you got to get your extra. Okay, the way we generate single sideband phone down here in the extra class portion of the band is we use a balanced modulator, that is a balanced modulator, followed by a filter. I got it, I got my mouth fixed. A balanced modulator followed by a filter, either the upper or the lower sideband filter. Now, what audio shaping network is added to a transmitter to proportionally attenuate the lower audio frequencies giving an even spread to the energy in the audio band. Well, this we use in an FM transmitter, and it's called a pre-emphasis network. And what audio shaping network is added at a receiver to restore proportionally attenuated lower audio frequencies? That's called a de-emphasis network. And you can really hear the difference with the de-emphasis network tuned in and turned on and off, listening to the subaudible tone of an incoming FM station. Listen to this. Listen carefully.
Good evening, Andy.
Now, hear that tone coming through?
Hey, good evening, Jed. K86.
Without?
Kind of nice now that Andy has his own caller.
And there's without, with,
I like that.
without, with, and
Yeah, not
without.
too bad. And just wait till he gets his own radio, too. Jeez.
So what the added de-emphasis network does is it adds back at the receiver the proportionally attenuated lower audio frequencies. Now, what's the mixing process? Well, the mixing process is the combination of two signals to produce some and different frequencies. What are the principal frequencies that appear at the output of a mixer? Well, that's the original frequencies, and here it is, anytime you see the word mixer, some and difference frequencies. What occurs in a receiver when an excessive amount of signal energy reaches the mixer circuit, in other words, you overload the mixer, well, you get spurious mixer products that are generated, and this is not good. What type of frequency synthesizer circuit uses a stable, voltage-controlled oscillator, programmable divider, oh, you know what it is, phase detector, loop filter, and a reference frequency source? That is the phase-locked loop synthesizer. Phase detector, loop filter, reference frequency source, programmable divider, VCO, voltage-controlled oscillator. It's all a PLL, phase-locked loop synthesizer. What type of frequency synthesizer circuit uses a phase accumulator, lookup table? Oh, there you go. That's a good keyword there, lookup table, digital to analog converter, and a low-pass Antilius filter. That is a direct digital synthesizer found in some of your more expensive radios. And the main blocks of the direct digital frequency synthesizer would be phase accumulator, lookup table, digital to analog converter, and a low-pass Antilius filter. That's the DDS, direct digital frequency synthesizer. What information is contained in the lookup table of a direct digital frequency synthesizer? Well, we look up the amplitude values that represent a sine wave output values. What are the major spectral impurity components of a DDS? Spurs at discrete frequencies are a problem, and they are problems with the spectral impurities that float around in poorly designed DDSs. But I'm happy to say that almost all new pieces of amateur radio equipment have wonderfully designed direct digital synthesizers with very few spurs at discrete frequencies. And the major spectral impurity components of a phased locked loop synthesizer? No spurs, but sometimes broadband noise. Not much, but a little bit there. What is the process of detection? That's the recovery of the intelligence from a modulated RF signal, usually using a diode detector. And what is the principle of detection in a diode detector? Rectification and filtering of RF. Now, since a diode only conducts for half of the AC cycle, it may be used as a rectifier. And by filtering out the radio frequency energy after rectification, detection is accomplished. The modulating signal is what remains. What does a product detector do? It mixes an incoming signal with a local generated carrier. How are FM phone signals detected? Well, we use a frequency discriminator. And the frequency discriminator is the circuit for detecting FM frequencies and FM signals. And how can an FM signal be produced in a two-way FM transmitter? again by using a reactance modulator on the oscillator. All right, 21 questions. Now it's time to take a well-deserved break. Go out there and pet the cat, feed the dog, wash the horse, wash the car. Come on back in a few hours. Not any vacation time yet, because we're almost to the end of this section, and then a few more, and then the big review on our final cassette course. Take a break. We'll see you back. And welcome back. E7F01. Digital frequency divider circuits, frequency marker generators, aspirins for your headache, and frequency counters. What's the purpose of a prescaler circuit? Well, we use those in frequency counters. It divides an HF signal so a low frequency counter can display the operating frequency. Now, how many states does a decade counter digital IC have? Decade. A decade is 10, so the answer is 10. What is the function of a decade counter digital integrated circuit? Well, the decade counter produces one output pulse for every 10 input pulses. That's why they call it decade. What additional circuitry is required in a 100 kilohertz crystal-controlled marker generator to provide markers at 50 and 25 kilohertz? Well, for 50 and 25, you need two flip-flops. Two flip-flops to take a 100 kilohertz signal and provide markers at 50 and 25 kilohertz. Now, if we had a 1 meg oscillator, 1 megahertz, and it's used to divide by 10 circuit to make a marker generator, what will the output be? Well, it'll be a 100 kilohertz signal with harmonics every 100 kilohertz with a divide by 10 circuit in a 1 meg oscillator. 100 kilohertz signal with harmonics every 100 kilohertz. Crystal controlled marker generator, that's a high stability oscillator that generates a series of reference signals at known frequency intervals. Sometimes called a marker generator all by itself, usually controlled by a crystal. What type of circuit does not make a good marker generator? That would be a sinusoidal crystal oscillator. One with a sine wave would not give us very many reference signals, so we would not use the sine crystal oscillator. We would rather use a high stability oscillator that generates a series of reference signals. What's the purpose of a marker generator? Well, it provides a means of calibrating a receiver frequency settings. And what does the accuracy of that frequency counter depend on? The internal crystal reference. And how does the frequency counter determine the reference frequency of a signal? Well, we do that by it counts the number of input pulses in a specific period of time. And the purpose of a frequency counter is to indicate the frequency of the strongest input signal called the near field, which is within the counter's frequency range. And how do we calibrate the counter to calibrate the radio? There it is. That's how we calibrate it.
At the tone, 3 hours, 16 minutes, coordinated universal time.
I had to calibrate my tuning there. WWV. Yeah. And here it comes beside the time. It's going to give us a precise frequency. So the purpose of a reference frequency such as WWV at 2.5, 5, 10, 15, and 20 is to allow us to calibrate our equipment. And I don't think I'm right on. Let me come down here. There we go. That sounds better. Now let me go between lower and upper sideband. Not quite. Pretty close. That's how we calibrate our high-frequency radio, is by going to WWV and then oscillating between upper sideband, there we go, and lower sideband. I think we got it. Close enough. Looks like I'm 80 cycles off. Close enough.
17 minutes, coordinated universal time.
And it even gives us the time of day. Okay, now let's take a look at question E7G01. What determines the gain and the frequency characteristics of an op amp RC active filter? Well, the gain and frequency characteristics are controlled by the value of capacitances and resistances external to the op-amp. And what causes ringing in a filter? Well, the filter shape as measured in the frequency domain. What are the advantages of using an op-amp instead of LC elements in an audio filter? Well, op-amps exhibit gain. The audio filter by itself would have insertion loss. And those little capacitors, what type of capacitor should be used in high stability op-amp RC active filter circuits? Polystyrene. The polystyrene capacitors are very stable and they will not vary even though the circuit board is getting warm. How can unwanted ringing and audio instability be prevented in a multi-section op-amp RC audio filter circuit? Well, we restrict the gain as well as the Q. And what parameters must be selected when selecting the resistor and capacitor values for an RC active filter using an op-amp? We need to look at filter bandwidth. The design of a preselector involves a trade-off between bandwidth and insertion loss. So that is what we have to look at with the preselector. Now, when designing an op-amp RC active filter for a given frequency range and Q, what steps are typically followed when selecting the external components? Well, we like to use standard capacitor values, and then we calculate the resistance because resistors of the nearest standard value are much easier to come up with and match them to a standard capacitor value. When designing an op-amp RC active filter for a given frequency range in Q, what are the external capacitance values usually chosen first, then the external resistance value calculated? Why that? Well, capacitors with unusual capacitance values are not widely available. So standard values are used to begin the calculations because you can come up with all sorts of resistor combinations. And what are the principal uses of an op-amp RC active filter in amateur radio circuitry? We use op-amp RC active filters as audio filters used in receivers. And where do we put those filters? We put them in the low-level audio stages. Wow, that was a brain buster. 45 minutes of practical circuits, but 7 questions out of 7 groups probably appearing on the exam. So go over this portion of the audio course. Know those flip-flops, know those amplifiers. Remember the monostable multi-vibrator switches momentarily, think of mono for momentarily, to the opposite binary state, and then returns after a set time to its original state. And the AND gate produces a logic 1 at its output only if all inputs are 1, and NAND is a logic 0 when only inputs are logic 1. OR gates, a 1 at its output if any input or all inputs are logic 1, and NOR gates produces a logic O or 0 at its output if any input or all inputs are a logic 1. Now, don't panic. Remember, out of all of this, only 7 questions will appear on your upcoming test. And on our final portion of this audio course, we're going to give you ways to remember some of these NAND and NOR gates and OR gates, and all about the truth table, a list of input combinations and their corresponding outputs that characterize the function of the digital device. All right, play this portion of the audio course over, about 45 minutes, and then we'll meet you, if you're on cassette, on the flip side of this cassette number 5, and we'll jump right into AC waveforms. Okay, take a break or a vacation. We'll see you back in a few.